Okay, 7.1, modeling situations with differential equations. Okay, it's going to be word problems. Okay, differential equations, what are they talking about? Differential equations are equations of derivatives. It's not exactly the word, but let's go with equations with derivatives. So I'm going to translate the equation of a derivative, and then I'm going to be able to I'll probably integrate it to figure out the original function or whatever we're trying to solve for. But the first kind of differential equation is just ones that are having some kind of directly proportional or inversely proportional relationship. Okay, so first definition, directly proportional. And if we just say proportional, we mean directly proportional. And there is some constant k, then A equals k times B. That's all it means. Directly proportional means they're related by multiplying by a constant. Okay, the second kind of proportional relationship we talk about is inversely proportional. A is inversely proportional to B. When we say that, what we really mean to say is that it is proportional to the reciprocal. Okay, so if A is inversely proportional to B, then it's going to be K times, and instead of times B, it's going to be the reciprocal of B, which is 1 over B, which we also could write as K over B, depending on which way is more useful in the situation. Okay, let's go ahead and try this. Okay, we're just going to be translating them pretty much. Okay, so for these examples, I'm going to write a differential equation that describes each relationship. If necessary, I will use k as the constant of proportionality. So sometimes I'm going to leave k in my answer, but when possible, I will solve for k so I don't have to leave it in my answer. Okay, I'm going to read the whole question and then we'll go back and translate it. Okay, the rate of change of y with respect to x is proportional to the product of t and the rate of change of w with respect to x. Okay, let's just translate. Okay, the rate of change of y with respect to x. Okay, when I hear rate of change, I'm thinking derivative. Okay, so the derivative of y with respect to x, they're just saying dy dx. dy dx. Okay, it is proportional, so it's going to equal k times is proportional. Okay, what is it proportional to? Okay, the product of t and the rate of change of w with respect to x. Okay, I heard rate of change again. That means derivative. So I'm saying the derivative of w with respect to x. So dw dx. Is that all they gave me? That they didn't give me any specific information, so I can't write the particular equation. So what am I writing? I'm just writing dy dx equals kt dw dx, and I'm just calling this a differential equation because it's the equation of the derivative of y with respect to x. Let's look at the next one. Okay, number 2. Okay, the force F of a spring on a trampoline can be related to the distance d it is stretched. The rate of change of the quantity of F with respect to the distance d is inversely proportional to the natural logarithm of the distance d. If the rate of change of F is 3 units per centimeter, then the spring has been stretched 0.2 centimeters. What is the differential equation for this situation? Okay, let's just read it. Okay, the force F of a spring on a trampoline can be related to the distance d it stretched. So it's going to be some equation with a F equals something with a d in it. That didn't tell me anything to write though. Okay, let's get to something interesting. The rate of change, okay, I hear derivative. The rate of change of the quantity of F with respect to D. Rate of change, the derivative of capital F with respect to D. So df dd. I'm using a capital D so it matches the equation. df dd is inversely proportional equals k. Inversely means it's going to be reciprocal, proportional to the reciprocal. So the reciprocal of what? To the natural logarithm of the distance d. So 1 over natural log, just ln of d. And it's just ln. It doesn't say rate of change. It doesn't say derivative. It doesn't say anything. Okay, so this is my general equation right here. It's a good differential equation. They happen to give me specific information about the function, which means I can try to get the particular equation. So then it tells me further, if the rate of change of f is 3 units per centimeter. Okay, so what are they giving me here? Rate of change. They're giving me derivative again. So the rate of change of f is 3 units per centimeter. Since it's centimeters, it must be df dt. Is 3 units per centimeter. Okay, then the spring has been stretched 0.2 centimeters. Okay, I need to go back and figure out where 0.2 is. 0.2 is the force F of a spring on a trampoline can be related to the distance d it is stretched. So it has been stretched 0.2 centimeters. So d is 0.2 when df/dd is 3. They're kind of giving me like an ordered pair. Okay, let me plug in the information I have and solve for k. Okay, so what do I got now? I have df/dt. 3 equals k times 1 over ln of d. D is 0.2 when df/dt is 3. Okay, let me times by ln of 0.2. So k equals 3 times ln of 0.2. In exact form, it would stay like that. If I'm approximating it, I'm going to put it in my calculator, and I'm going to leave 4 digits. Truncate or round 4 digits. Okay, now that I have the k value, I can go ahead and substitute this in for k here so I can get the particular differential equation. Okay, let's plug it in. So df dd is going to equal to k times 1 over ln d. So k times 1 is just going to be k. I'm going to put it in the numerator. Over ln d. Okay, and then this is my differential equation. It's the equation of a derivative, and I solve for k whenever I possibly can. Okay, let's try one more. Okay, Tim is swimming in a straight line across a lake. His position from the starting point is given by P of t, where t is measured in minutes since the start of his swim. During the first 30 seconds, Tim's acceleration is proportional to the cube root of time since the start of his swim. Write a differential equation that describes this relationship. Okay, Tim is swimming in a straight line. No information. His position from the starting point is given by P of t. So I know I'm using P of t for something. P of t is his position. Okay, during his first 30 seconds, Tim's acceleration is proportional. What is acceleration? Okay, position is P of t. If I want his velocity, that would be P prime of t. If I want his acceleration, that would be the second derivative of P. Hold on, I'm going off my screen. Let me erase that. So I'm thinking acceleration is going to be the second derivative of P. Okay, I'm going to write it as, so it looks like the other one. So I'm going to write it as the second derivative with respect to time. So d squared of P with respect to time, dt squared, acceleration. Second derivative of position is acceleration. Okay, let me keep going. Is proportional k to the cube root of time since the start of his swim. What variable is time? Is it t? Yes, t is measured in minutes since the start of his swim. So the cube root of time. Write a differential equation that represents this relationship. Okay, this is the best I can do, this general equation, because they did not give any particular information that I could plug in to solve for k.